camera. Today, this is the second event of MATUROLIFE dialogue series, and then we are going to talk about what makes a product smart and innovating with Smart Textile. My name is Gülay Özkan. I'm founder of Get Strategic Consultancy. I'm very happy to host two very top experts in their own field or from Europe in this event. Andrew Cobley, he's principal investigator of MATUROLIFE project, and he's also a professor at Coventry University, which I'm going to give a bit more details in a minute. And Neil Chilton, he's a technical director and a technical director of printed electronics, and he's also the printed electronics lead at MATUROLIFE project. And both Andrew and Neil are from UK. This is, as I said, this is our second event. The first event was about more towards the creative people, how they can join large-scale projects and how they can achieve. We shared our experiences on Clubhouse last month, and the details of this conversation you can find it on our blog. And during the pandemic, we have hosted several events, and then it was all from different expertise. For example, we had a joint event with the MIT Solve program, and then connected with that, we also had an event with the ING on new working models for changing employee needs. All these sessions, all these events you can find on our YouTube channel, also on our blog. And we are very sensitive about sharing high quality content. So you can reach again through our blog, our LinkedIn page, our Twitter, and also on our YouTube channel. I'm going to today, I'm going to talk about a little bit about our company in case we have some people that are not maybe familiar with GETS. And then Cobley, again, he's the principal investigator of MATUROLIFE project, and he's a professor of electrochemical deposition and the leader of the functional material research group at Coventry University. He's one of the top experts in his field in Europe, I believe probably worldwide as well. So I'm very privileged to have him as a speaker today. He will be talking about smart textiles. I mean, we got a lot of questions about, I mean, as a design company, of course, we mentioned that the MATUROLIFE project is about smart textile innovation, but of course there are we get many questions about how the smart textiles can be used in practical smart products. So that's why we are hosting this session. And then after Andrew, Neil Chilton, he's the technical director and printed electronics lead at MATUROLIFE. He's one of the most talented, maybe the senior person I've ever worked with. So I'm very privileged again to host him here. He's very modest. Of course, he's not going to say that, but I'd like to just tell many people in my network. And then after Andrew and Neil share their perspectives, I mean, Neil more will talk about how to, of course, insert smart products embed in smart products. Also, I'm sure talk about the what makes a product smart with maybe electronics or with in different dimensions. Then we will have a question and answer session. Please write your questions on the chat panel. We will receive it and we will organize them and share with Andrew and Neil. So and then we will have a brief closing. Very briefly, GETS is a strategic design consultancy. And we are 13 years old. We have touched the lives of people in 35 countries, and we have developed solutions in many different industries. And also we are proudly to be invited in 27 countries to share our experience. We have worked with several clients. Some of them are multinationals, museums, banks, non-profits in different continents. And also universities. So I'm very happy that we are touching many people in different countries. So, and we have been listed in several top tier, together with top tier brands, both in Europe and the US. So this is something that we care quite a lot to present our work in the international space. And then recently our work was recognized by the Design Management Institute in Boston in 2019, and in 2020 we were part of the list like nominated by Fast Company and also Microsoft. And then today's topic again, this is a MATUROLIFE dialogue series, MATUROLIFE project. I'm sure it would be also nice to hear from Andrew as the principal investigator. MATUROLIFE projects, basically we aim to design and develop smart products for older people. Getz is a lead design company in the project. This project is funded by European Commission, and from design perspective, this is quite a complicated project, and then we run all this work in 7 languages in 9 countries, and it has been quite a large operation, but we are super proud of the work, and I believe we all did very well as 20 business partners. And then now I will give floor to Andrew, and he will share his experience about the Smart Textile, and basically we can also have questions meanwhile.
I couldn't unmute my screen for a moment. Okay, well, good afternoon everybody, and good evening, I guess, in Turkey probably. So as you've just heard, my name's Andrew Cobley. I'm a professor at Coventry University, and I'm going to give you my perspective on what I think makes a textile smart. Before I do that, as Gule mentioned, I'm the principal investigator. My computer's about to switch off. I'm the principal investigator for MATUROLIFE, which is a €6 million project funded by the European Union and led by Coventry University. So we have 20 partners from 9 EU countries. The project is truly cross-disciplinary. As Gule has mentioned, we have, if you like, 3 distinct areas really of the project. There's a very strong design side to the project. We've used user-centered design. We've carried out co-creation workshops, etc. On the materials side of the project, we've been carrying out electrochemistry, materials science, we've been doing printing, etc. And using all these disciplines, they've really come together with electronic integration. And the aim of MATUROLIFE is to produce 3 prototypes in the area of assistive technology for older adults, 1 in footwear, 1 in furniture, and 1 in clothing. Okay, so what makes a textile smart? So this is an example of some work which Coventry did with the National Physical Laboratory a few years back. And what you can see we've done here is we've metallized this glove. So I think this gives quite a nice example how you can quite simply add some functionality to an item that is already made. So in this case, the metallized areas on the textile are acting like a sensor. So basically, if you put your hand into this glove and you clench and unclench your hand, the resistance of these tracks will change, and you can pick that up on this tablet via Bluetooth. And obviously, this isn't particularly sophisticated. We've just got wires here for connectivity. But what's happening here is that we're using the textile material now as a dielectric. So anybody who's familiar with printed circuit boards will know that you use a dielectric material on which you have copper electronic tracks. And what we're doing here is, instead of having a rigid PCB material, we're now using the textile actually as the dielectric. So using an approach where we can add metallization to a textile, we think will give better integration of electronics into a textile. Okay, so there's a number of methods of selectively metallizing textiles. I'm not going to go into detail of all of them. There may be some missing here, but given the time, we can't really go into all of them. But I'm going to talk briefly about electrochemical methods, and in particular electroless plating, and that's the method, in fact, that we've used mainly in MATUROLIFE. But then another common technique is printing of conductive inks. And again, I'll briefly talk about inkjet printing and screen printing, but this is really the area of expertise of Neil. Again, another approach is to use physical vapor deposition, and you can also integrate conductive threads, fibers, and yarns. So, as I mentioned, electroless plating is actually the method we've used in MATUROLIFE. It's electroless plating. It's a well-known process that's been used for probably 40 to 50 years now, and it's commercially available and it's relatively low cost. Now, the idea, what we like about electroless plating, is that the aim is to actually coat the fibers within the textile with a relatively thin layer of copper, so around about 0.5 to 2.5 microns of copper. And in this way, what we're hoping to do is to produce a truly multifunctional material. So the textile should still feel like a textile, because we've only added a very thin layer of copper, but we've now added the functionality of a metal. And this shows a scanning electron micrograph of fibers that are plated within the textile. This is false color, because under SEM it's normally black and white. But you can see here that the fibers are fairly well coated. And this is a picture which I really like, which shows like a section through one of the fibers. And you can see the fiber of the textile is here in the middle. And you can see we've got a coating of electroless copper around the outside. It's fully encapsulated. So with electroless plating, we can plate the common metals are copper and nickel, but you can also do silver and gold. Now, I know this is a non-sort of technical webinar, I believe, so seeing this, don't worry, I'm not going to go into depth about the electrochemistry. What the main take home that I want here is that electroless plating requires a catalyst to work. So first of all, we need to deposit a catalyst wherever we want metal to plate. And this means that it's a good method for selective deposition, because wherever we deposit catalyst, we will get plating. So if we deposit catalyst here, here, and here, we will only get plating here, here, and here. So it's a good way of producing selective metallization, producing lines, tracks, whatever really. And in MATUROLIFE, what we're doing is actually printing a catalyst. And this is what I'm showing in the next slide. So working with our partners in MATUROLIFE, particularly Plasmachem and Printed Electronics, we've developed a printable catalyst. in the project, and you can see here the catalyst being printed. We've also set up a pilot Electroless Plating line at our partner Burton Aubert in Paris, and you can see these panels now are actually being plated in the Electroless copper, and these are the final products, if you like. So these are actually, this is actually circuitry that's going to be used on the insole of our footwear prototype for MATUROLIFE. Okay, so another approach is to print conductive inks. So conductive inks contain highly conductive metal particles or flakes of materials such as silver, gold, copper. This is a printing method, so you can generally get very good resolution. But one of the drawbacks, if you like, is that the inks do need to be relatively low viscosity. But it does lend itself to high volume manufacture, reel-to-reel manufacture. And you do need, generally, you do need some sintering or heat treatment to get good conductivity. So the reason we need sintering is that in the ink, the particles generally, so often you use a dispersion agent, and then by sintering, you will remove these or degrade these dispersion agents. That allows the particles to come together and agglomerate, and then you get good conductivity. Screen printing, probably if there's anybody here who works in the textile industry, they'll be very familiar with this. And this is essentially the same process. So you have a screen frame, you pull the conductive ink across the frame using the squeegee, and that deposits where there are gaps in the frame, and you're left with ink deposited in the pattern of the screen. One of the advantages of this is you can use much more viscous inks, and you can have a higher concentration ink, giving you good conductivity. So in this case, sintering is not so critical. And here are some samples that we produced in MATUROLIFE. These were produced by Printed Electronics using a silver ink. They were used to produce what we called the NFC demonstrator. Physical vapor deposition is a physical method of depositing generally metals, but you can deposit ceramics as well. It can produce multi-layer coatings, and one of the advantages of PVD is that you don't need chemistry. So when I discussed the Electroless process earlier, one of the disadvantages is that you do need to process the textile through various chemical processes. So you do have hazardous waste involved. Whereas this method, as I say, it's a physical method, so you don't produce any waste chemistry. And one of our partners, IFTH and MATUROLIFE, have developed a roller system which can be put into a PVD machine, and it can be used to deposit various metals such as silver, aluminium, and titanium. And here's some examples again produced for MATUROLIFE. So this was these are aluminium on textile using PVT, and they use some photoresist to selectively deposit the metal. And finally, just briefly talk about conductive threads, fibers, and yarns. So I've seen that my colleague, Dr. İlkem Göçek, is on the line today from Istanbul Technical University. So big thanks to Ikalem for sending me these pictures. So these are knitted textiles. So the one on the left, we have a silver coated yarn, which has been knitted into polyester. And on the right, we have, again, a silver coated yarn, but this time knitted into polyamide. So obviously this is another approach to make textiles selectively conductive. Okay, so in a very simple way now, if we've metallized our textile, can we say that it's smart? Well, now we've got metal on the textile, it can now carry current. So as you see here, these are some test parts from MATUROLIFE, and you can see that if we measure the resistance, we get a very low resistance. We've made it conductive. And another example here, just using a very simple circuit. So our textile, as I mentioned right at the start, it can be used now as a connector, an electronic connector. It could also be used as an aerial. It can carry signals now to some extent. And also it could be used for shielding. So if you use electroless nickel, it can shield from RF signals. It can now conduct heat, again, because we've now made it, we've metallized it, it can conduct heat. So in this example here, we applied a current of 0.75 amps, waited a few minutes, and it quickly heated up to around about 150 degrees. And very topical, if we've now coated our metal, particularly with copper, it's certainly now going to have antibacterial properties and probably antiviral properties. I was hoping to be able to tell you today some stop press that we had proved it was antiviral, but I'm afraid those experiments are still going on at Coventry. But essentially, copper is a well-known antibacterial. So if we have some copper on our textile, we have, for example, a droplet that contains some bacteria, then the metal ions from the deposited metal can be transported into the bacteria, causes membrane rupture, can produce toxic radicals, and leading to DNA degradation. So potential applications for this, you could have antibacterial, antiviral textiles for various healthcare settings, gloves, face masks, gowns, bed sheets, soft furnishing. And I'm sure people can think of many other potential applications. If we have selectively metallized textiles, so if we have two copper tracks, for example, as I've tried to show here, it could, in theory, detect moisture now. If we have a moisture droplet between those two tracks, then the resistance is going to change between those two tracks. So this is a very simple moisture sensor. So potential applications here as sweat detection. So that perhaps could be useful if you're trying to detect stress in somebody. Wound dressing, so leakage through the wound dressing. Bed sheets, unfortunately, if you patient has incontinence, this could be a way of monitoring that. And again, I'm sure you could think of many other potential applications. And it could also now act as a stretch sensor. So this is, again, going back to some work we did with the National Physical Laboratory. They developed this stretch rig. And what we found was that when we had a metallized textile, when we stretched it, the resistance increased. And then as we relaxed it again, the resistance decreased again. So if this can be done in a reproducible way, this is essentially a stretch sensor. So potential applications could be in compression bandages to monitor how an ulcer is swelling, for example. It obviously could be used in body movement and activity monitoring. And obviously as your chest moves in and out for breathing, it could be used to detect that as well. So to wrap up, hopefully I've shown there are a number of metallized textiles. Once the textile has been metallized, I would suggest it's now become multifunctional. And now we've got metal selectively deposited. We've got several additional properties. So it can now conduct electricity, it can conduct heat, it can act as an electronic connector, and even very basically, it can act as a sensor. So is it now smart? I'd say it probably is. So thank you very much for your attention.
Thank you.
Thank you, Andrew.
Thank you. Good. Okay. Well, thanks everybody for joining the call. So my name is Neil Chilton. I'm the technical director here at Printed Electronics, and we started back in 2006. So I've been doing this for quite a long time. We haven't always been doing wearables. In fact, when we started, our main aim really was working on doing more conventional electronics, but by doing it with printing. So we use the technologies that Andrew's already talked about. We do inkjet printing, screen printing, 3D printing, nozzle deposition, wide range of printing technologies. But actually fairly early on in what we started to do, we started to get involved in wearables, and we've worked with a number of major partners in this area, large companies and small areas. And the MATUROLIFE project has been a really interesting project to be involved in. And we've been doing that now for over 3 years, but time has really gone flying by, actually. We'd like to do it for longer, but we can't do it forever. So what we're going to talk about is wearables and smart. So what is wearable technology? Well, there's many definitions out there. If you go on Wiki, this one from slightly edited from Wikipedia is not a bad one. It basically focuses on the right thing in my view of this, because the key here to wearable technology is it melds those two things together. It's wearable, but it's also technology. Just the fabric on its own is not that smart. It does things, but just on its own, it doesn't do enough to make people believe it to be a wearable technology product. It's a wearable product, but not necessarily wearable technology. So that's a wearable technology. And I always like these Google Trend graphs you can just get on Google Trends, and you can just see how many people search for things. This is from 2004 to the present day, and it seems around about 2009 or so. It's a massive increase in people interested in wearable technology, which is, you know, driven by Apple Watches and all the Fitbits and things like that people have called wearable technology. The key question is, what do we mean by smart? Now, smart is one of those words you can put in front of another word to make it sound better, even though it isn't. Like in the UK, we have these smart motorways, which are not really very smart at all if ever you've driven on one. So it's one of those words which sort of defines anything you really want it to. It's a bit of a marketing word, really. But in our case, what we're focusing on here is how we implement multiple technologies together. So for us, wearable technology and Internet of Things, those two things go together really well. Both of those require connectivity. They both require, in the case of Internet of Things, that's a wireless connectivity, and both of those really get back to being conventional electronics. Somewhere in the mix of things, there is a little, you know, Wi-Fi transmitter. So all of these things kind of, you know, it's very much the right time to be talking about over the last, you know, 5-6 years. It's the right time to be talking about these things. But in the case of smart, that's becoming, smart itself as a word is becoming a kind of overused buzzword, actually. And if any of you have the opportunity to subscribe to this magazine, it's quite a good one, actually, if you're interested in this area. It's OPE Journal. It's run as part of the Organic Electronic Association, of which we're members. And this particular current issue focuses on smart living and mobility, and has a number of interesting articles in there. So that's just a bit of a plug for that magazine. It's worth having a look at. Now, MATUROLIFE, the aim in MATUROLIFE really is to use the collaborative design methodologies which Cobley has already outlined and Andrew's already outlined, bringing together engineers, which I'm clearly on the engineering side rather than the design side, bringing engineers together with the design community and designing things which are not only technology driven, but they're also user driven. So the great thing about the MATUROLIFE project is it focused on assisted living. Now, I thought if you do a Google Trends search for assisted living, I thought you'd also find a peak for that in, you know, just a few years ago, but it seems that realistically, assisted living has been fairly flatly searched for a long period of time, except for when the pandemic started. And when that started, there was a massive peak here, you can see at the end. But anyway, so it shows that people's interest in assisted living is high and remains high. It's far more interest, there's far higher there than wearable technology in scale. And that's good because it means that what the design teams and what the people-focused side of MATUROLIFE has brought together is a viewpoint of what people actually want from a wearable electronic product. Now, in wearables, this is a really old picture of an old Apple Watch, but in wearable electronics, you might well view a Fitbit or an Apple Watch as wearable electronics. None of this is fabric. There's nothing in here which the strap probably, you know, the strap is soft. But all of this really is a really quite an incredible ability to jam together components, electronic components in a small space. And all of this is focused on the semiconductor technology world and the printed circuit board manufacturing world in order to get extremely high density of connections. So all your processing power, all your battery, the screen, the touch sensitivity, the haptic feedback, the oximetry pulse sensing, all of that is all conventional electronics. And that's a really important definition. That isn't going away. As much as we would like to be able to take a fabric and impart into the fabric a lot more smarts than we've done so far, the reality is that, although I'll cover it a little bit later, the reality is that we're still going to rely on this sort of thing for a long period of time. So one of the really important parts of wearable electronics is how you interface the conventional electronics end of it to the fabric end of it. So bear that in mind as you think about applications for smart and wearable electronics. So within MATUROLIFE, the aim of the project that was defined by asking people what they want rather than telling them what we have, came up with 3 prototype products. And the first one is the one that we're most involved in, and that is the Smart Shirt, a shirt which embeds a number of things, but first and foremost, it embeds heating. Andrew talked about how you can use dual heating. You can put a current across a track and it becomes a heater. That's done in motorbike jackets, it's done in gloves, it's done in boots, it's done in areas where generally it's quite easy to do if you've got a thick jacket. So something like a leather jacket for motorbiking, it's very easy to put a heater in there because you've got lots of space and it doesn't matter if it feels a bit stiff. But what we wanted to do in MATUROLIFE was to put a heater in which was much more soft, much more flexible. And I'll cover that a little bit later. In addition to that, we also, some of the pictures Andy showed of the shoes, the sensors that we've embedded into the shoes, they are to sense pressure. And by sensing pressure, you can tell whether somebody is standing up straight or standing up with a little bit of a balance problem or is at risk of falling over. And so the sensing of balance and pressure, that's something which the shoes deliver. And I'm not going to cover that here. And the other thing that we made in the project is an intelligent sofa, which also uses fabric as a occupation sensor and other sensors it can detect things like moisture as well. So, so the sofa is also smart. So I'm going to focus though on the fabric for the t-shirt or shirt. There's a really big difference between fabric and electronics. So Fabrics are comfortable, they're soft, they're ubiquitous, they're washable, they're incredibly cheap. And they have a nice feel. You never complain about how many times you dropped your t-shirt and it doesn't work anymore. Whereas with electronics, you've got completely different use cases. They're generally fairly rigid, still ubiquitous. We've got electronics everywhere. They don't like water very much. They're pretty cheap actually, but only by virtue of the immense changes in global contract electronics manufacturing over the last 20 years. But electronics gives you human machine interfaces, it gives you Wi-Fi interfaces, but they all need power, need a battery. They need to be connected somehow, probably to the internet. So these two things don't necessarily go together all that well when you put it on paper, but what we're focusing on in the project really is to join all the interesting stuff from both sides of this plot together to try and come up with something which is actually useful. And it's not been that easy. There's a lot of challenges in this. These yellow highlighted parts are the bits we're really focusing on to try and make the shirts that we're making in MATUROLIFE interesting and useful. So fabric-based electronics, I mentioned we've been doing this for many years, and this is something we did quite a number of years ago. This is let me just turn that off. This is a fabric-based display. And the fabric here is a metallized fabric. It uses the same plating technology that Andy talked about, but done in a slightly different way. And what we did onto this is we placed a number, 144 LEDs, and each of those LEDs is a addressable display LED. And so we could use it for displaying colors, displaying text. And the reason that the LEDs are facing against the wall is because it's it's too bright facing the other way, and B, I got the program the wrong way around, so it has to be looked at in reverse to see properly. But as you can see, it's nice, it's soft and it's flexible and it's fabric. So you could say that's smart textile. But really, the textile is just conductive. Right? All it's doing there is being conductive. The smart is in the components, the electronic, thankfully being shrunk to smaller and smaller sizes all the time. And it requires external power and all of those things. So it's partially there towards where we want to go. But what we wanted to do within MATUROLIFE was to take that concept a little bit further and to implement a number of different parts to the smart clothing. So with that, what we wanted to do is get rid of the wire. On this one, there's a wire hanging down here to the controller. Here, we want to make it entirely embedded in a wearable product. So here's the heater. The actual soft fabric connection parts, and I'm going to show you a real part. I'm going to turn off the presentation and actually show you some real parts later after this. So this is what it looks like. There's some interesting sensors that we've developed in here. This part, the little white 3D printed case thing down here, that's where all the intelligence is. That's the controller. But we've got a heater, we've got sensors, we've got temperature sensors, which are quite nice and accurate, and touch buttons, capacitive touch. So, but the key thing really is that all the really smart stuff, the bit that you will be able to interact with in the mobile phone app, because that's essentially how we want to interact with the world now. We just want to interact through a mobile phone or have it relatively autonomous running. It's all through this. This is the module. And this, if anybody's familiar with that, that's an ESP module. So Wi-Fi, Bluetooth compatible. This is where the haptic sensor goes. There's a battery in it. There's all the usual things that you would expect from any electronic module. And it's got a flexible electronic part to it as well. And when we set the temperature of the heater to the correct temperature as we define it through using the module, it heats up and we get maybe 40 degrees Celsius from this. That's a nice body temperature type of effect. So the heater itself is placed in the middle of the back, which is where the users said they wanted it. Makes them feel nice and warm, makes them feel like somebody's close by. So it doesn't heat the whole of the t-shirt. And that's a really important point, because we could have made this heater cover the whole of this surface area. But heating is not a very efficient, heating requires a lot of energy in order to get that heat energy through vibrational energy into your body to recognize it as heat. And so what that really means is you can't have a battery big enough. You could have a huge heater on here, but you'd need to plug yourself into the wall. So we always wanted to make this self-contained, and therefore we're actually quite limited in battery life. And a battery life for a mobile phones are incredibly efficient in their use of heating, in their use of batteries. But the thing they try and avoid doing is heating up too much, because heating is one of those things that just wastes your battery. And effectively, that's what we're trying to do here, is we're trying to use a battery to heat this thing. So, so we've implemented heating, and we've needed to do that in a very energy efficient way. So how do we make these parts? Well, we make them by printing. So this is one of the parts on our printer. This is an inkjet printer, and I wish this was real time, but it's clearly not. So this is it printing a copper material onto a fabric. That copper material then is plated, as Andrew has already discussed. And that is then, that panel then is cut and embedded into a wearable t-shirt, or actually long sleeve shirt, actually. And what we've got by printing is we've got connectivity, we've got conductivity. So we've replaced the wires. There's no wires there. Everything is in the t-shirt. We've got the ability to sense things like touch, capacitive touch, potentially pressure too. And we can do pressure using a different material. And we can, of course, do heating. And we rely on the real electronics, which we have to join in a very clever way. The real electronics has to join the fabric electronics in a really clever way. Now, what I'm going to do now is just stop sharing this, and just I'm just going to change my video over to show you some. This is an example of the shoes, and you can see here the tracks that have been printed and plated. What I'm going to do is I'm just going to change over to a different camera, which is a microscope camera, just a small USB microscope camera. So I don't know if you guys can like pin my video or something, so then it just appears bigger for everybody, or you can do it yourself if you wish. So this is textile, and this is what we've got to print onto. This is our substrate we're going to print onto. For us, this is a completely different sort of substrate from what we normally print onto. We normally print onto smooth, easy to print on materials, but here, this is the print. Okay, so this is the print and plate. So you can see within the fiber here that there are unplated areas and plated areas. So as Andy said already, you could do this by weaving. You could weave in your conductive threads down here, or do what we're doing, where we're printing to plate the part. And what's really nice is, if I can get this the right way around, yeah. So when you magnify the view up really well, you can see that you really are plating all of the fibers, and that means that this is robust enough to be stretched. So when we stretch the fabric, it doesn't break those conductive elements. So I'm going to go back to my normal video. Well, normal, it's got me in it, so it's fairly normal. But and then go back to the screen share. So that kind of gives you a view a little bit. So that's what I'm trying to show on this view here. That what we're aiming to do here is to make a very robust connectivity across the textile. So what we're avoiding doing is just printing on the surface, because if you just print on the surface and then stretch it, it'll break. So this is why this project has been important. So why would you use fabric-based electronics? You would use it because you want something to be soft and flexible, stretchable, washable for sure. Now, I've put question mark after washable because if you wash these materials, they do degrade in the washing process, but you can get maybe 5, maybe 20, maybe 30 washes out of these things, depending on what's required. But it does have some weaknesses, and the weaknesses are that you always need external power. You've got very limited electronic functionality from the fabric itself, and you need to join it to conventional electronics. So where is the technology as a whole going, whether we're involved in that or whether it's other people involved in it? Well, one of the key areas is to embed power into the fabric itself. And there's a lot of groups working on that. We've done fabric-based batteries. We print batteries onto fabric, and they work really well. They don't last very long because they're not like a, you know, they don't recharge. They're not like a normal lithium cell or anything because we're using safe materials. And most people are focusing on supercapacitor applications. And if you do a few Google searches, you'll find people looking at these very carbon-rich materials for supercapacitors. So that's one way of getting the power in. You charge up your T-shirt or whatever. But the other way of getting the power in is to reduce the energy requirements of your circuitry and use energy harvesting. So you can use effective, like when you rub a balloon on your shirt and you stick it to the wall, that's a triboelectric effect. You built up static electricity. It's still electrons, and that can drive circuits. So you can use triboelectricity, you can use electromagnetics, you can use piezoelectrics. And all of these things are really being progressed quite heavily at the moment. And that is a way of making autonomous smart fabrics and smart textiles. And we're doing a project at the moment, which I can't talk about, with a major manufacturer, where we're looking to embed some quite interesting technology into a particular fabric. And then really where you want it to go eventually is to have truly wearable stuff. And John Rogers' group in the US have done some really interesting stuff. If you have a search for the Rogers group, you will see some really interesting stuff where electronics can be embedded directly onto the skin. And in that case, of course, it has to be autonomous. You can't have a battery on there as well. You have to have it self-powered, or at least RF, radio frequency powered. And these are things that are coming, but coming in the right area. This is not for you know, general day-to-day usage. This is for medical applications or particular sensing applications. So that covers the presentation that I wanted to give there. And I just wanted to sort of say thank you to all of the partners. But what I'm going to do now is just show you some of the stuff that we do. So this here is a fabric-based electronic product. It's actually using screen printing. And this is a multi-sensor array for a medical application, which is quite neat and quite large and quite interesting. We also have done over many years, actually, Andy mentioned antennas. Fabrics can be used in antenna applications. This is a Wi-Fi antenna, just based on fabric. So just simply 2 layers, and works as a pretty reasonable antenna for Wi-Fi. The display I showed before, we have a big one of that. This is a much larger LED-based display that is fabric-based. You can perhaps see if I wobble it in the right way. So all of this is fabric-based. The electronics is built in. We have a whole bunch of other stuff as well, if anybody's particularly interested. So that covers a few of the things that we sort of focus on, and how we've maybe implemented some of that in the MATUROLIFE project. But I want to make sure there's a few minutes left for talking and asking plenty of questions. So I'm going to finish there, if that's okay.
And thanks so much again, Andrew and Neil. It was such a great honor to host you as speakers.